The second part now is on nitrogen balance. This part is a little bit technical. Some things are a little bit more difficult, but I hope that you will understand what we want to say. Nitrogen is linked to proteins. Proteins could be used to generate energy, which we explained in the previous lecture, but it can also be used to build up body tissues. Building muscles, for example, is directly linked to the physical presence of protein, synthesis of protein, and muscle protein in humans. So what we are explaining now is mainly intended to understand what we actually need to build up body tissues. So nitrogen can be used for many compounds, the protein, bile acids, creatine, glutathione, different types of porphyrins, choline, nucleic acids. So there's a lot of compounds in humans that actually require nitrogen. And that's not only protein, so it goes beyond protein. The balance of nitrogen is the same as with energy. So you look at what is coming in, you look at what is excreted, and the difference between the two is the balance. If it's positive balance, then it means you take up more than what you lose. Negative balance, you lose more than what you take up. And a nitrogen balance equal to 0, the two are in equilibrium. The balance study was the original studies which are still used today to determine protein recommendations in humans. But more and more, people start to understand what is going on within the human body. With a balance study, you will not know that, because you just look at what is coming in and what is going out. The body is a black box. But if you open the black box, then you could understand more about protein turnover, how protein is broken down and built up again, oxidation of amino acids, production of urea, excretion of nitrogen. And you can study that during fasting, eating, postprandial, as well as post-absorptive states. And all these processes nowadays, as you know from chapter 4, can physically be measured in humans. And so we know how fast protein turnovers occurs when you are fasting, when you're eating, whether you are in postprandial or post-absorptive states. The balance itself is a little bit complex. So you can see here the amino acids that are circulating in the blood. They are converted into body proteins. The body proteins are broken down into amino acids. And this cycle, let's say, is actually called turnover. So the continuous breakdown and building up of body protein is actually called turnover. The amino acids can then be converted into carbon skeletons, as well as amino groups. This is the transamination reaction that we saw in chapter 4. And from that, you build urea in the liver, and the urea goes to the urine and is excreted from the body. The nitrogen itself can also be directly excreted in urine, but it can also go to the colon, as you can see here, the urea. And in the colon, it can actually be used by bacteria to produce bacterial nitrogen. And this can go out by fecal material. And so be very careful if you would do a digestion study in which you are measuring nitrogen intake and nitrogen loss in the feces. Don't think that the nitrogen in the feces is exclusively coming from the diet. It could also be that body protein is broken down, gives you amino acids, is turning into urea, goes to the colon, and from there is going to the fecal material. So fecal material for nitrogen metabolism is quite tricky because there are many components from nitrogen that are coming in there that have actually nothing to do with nitrogen in the diet. So be careful with that. But generally speaking, if we would look at nitrogen balance, you would look at intakes, which is coming from the diet, and the losses is mainly fecal material, urinary losses, and some other losses, and like, for example, hair or skin or nails. So all these losses are quite small, and usually we would take a standard correction factor for that. We're not going to measure it. It's just correction, but we do measure urine and fecal losses. Here you can see the values. So urinary losses is about 80%, fecal material 10, 15%. So we're already talking here about 95% of the nitrogen losses. That is either urine and fecal material, and all the rest is less than 5%. So that one we can take stable or constant during the calculations. Here you have a balance, which is called the nitrogen balance, which has been done with, I think it was a study on primates, on chimpanzees, whereby they put them in a metabolic cage so that you can exactly measure the food that they take in. And you can also collect all the excretion products. So you collect the urine, you collect all the fecal material, and you analyze it for nitrogen. So on the x-axis, you can see the nitrogen intake of the animal in grams per day. On the y-axis, you can see the balance, so the difference between the intake and the losses. And you can see that for two different proteins, lactalbumin, which is an animal protein from milk products, and soybean protein, which is a plant-based protein. And you can already see that there's a difference between the two in terms of protein quality. You can see that by looking at the inclination. And so it's much more steeper here in lactalbumin than in soybean protein. So the more steeper it becomes, the higher the quality of the protein. This also means that the connection point here between balance equal to 0 is actually moving from the right to the left. And the more closer you come to the left axis, the more higher quality protein you get. So you can actually start here on the left at 0 intake. If we don't take in any nitrogen from the diet, then the balance is negative, which is quite logical because the animal is just losing nitrogen and is not gaining nitrogen from the food. So the balance is negative. And there's no difference between the albumin study and the soybean study because there's no protein involved. It's only the animal as such. If you then start feeding the animal, then you go from the left to the right on the curve. The animals will take up more protein. And then you see that the balance is slightly moving upwards until it reaches the value of 0. And you can see here that the amount of nitrogen or the amount of protein that you have to take in to reach nitrogen balance equal to 0 is smaller for lactalbumin than for soybean. So it means that lactalbumin is a high quality protein and soybean protein is a low quality protein or lower quality protein because you need more protein to get balance equal to 0. Here you need less protein to get balance equal to 0. Yeah, so the connection point with balance equals 0 or the inclination of the curvature tells you something about the nutritional value of a protein, which is usually higher for animal type proteins than for plant-based proteins. So based on this technique, which we call the nitrogen balance technique, today we determine the recommendations for humans. So you start with the obligatory nitrogen losses, which is what we already said, the inclination here at the x-axis. So here at the y-axis, the inclination you get when you don't take in any nitrogen, this is called the obligatory nitrogen losses. You will lose them anyhow, independent on whether you take nitrogen or not. You can do that by looking at the protein-free diet, and the nitrogen that you will measure there is the metabolic nitrogen, which you will find in the fecal material, and the endogenous nitrogen that you will find in the urine. The total amount there is 54 milligrams per kilogram body weight per day, or if you convert it into protein, it becomes 0.34 grams of well-balanced protein per kilogram body weight per day, which is equivalent mostly to an animal-based protein like milk or meat. So not plant-based, it's mainly animal-based. So what is then the requirements that you need to take the intake or to reach a balance equal to 0? this is actually the so-called requirements. And so this is actually that you need to give to a person in order to have nitrogen balance equal to 0 and to compensate for the losses of nitrogen during the day. It's also called the factorial method that we explained in the first chapter of the course notes. If we look to the values, then we reach a value of about 0.6 grams per kilogram body weight per day. So from 0.34, you go to 0.6 by taking into account the utilization of well-balanced protein. So as soon as you increase the intake of protein above, let's say, the obligatory nitrogen losses, then it seems that the losses will be less extreme. The more nitrogen you take in, the less relative losses you have, because the body is probably gonna, let's say, have other types of losses when you take in more nitrogen than when you take in few amount of nitrogen. I'm not sure if I'm expressing myself well. I will explain again. So if I don't take any nitrogen in by the diet, so obligatory nitrogen losses is, in this case, there. I can measure it in the urine and in the fecal material. So probably the losses are maximum there. No, the losses are minimum there. It's minimum there because I don't take in any nitrogen. Yeah, if you don't take in any nitrogen, then you will have a low amount of losses because the body is trying to recover as much as it can. It works in a very, very efficient way. However, if I start taking in nitrogen from the diet, then the losses will become less efficient. There's more nitrogen available, so I don't have to be so strict. So it means that I will not utilize all my protein well, so my utilization will become less than 100%. In the first case, the utilization is almost 100% because I don't have any new protein coming in. In this case, when there's enough protein, the utilization factors will be less. And taking this utilization into account, I can go from 0.34 to 0.6 grams per kilogram body weight per day that I will need to normally get balance equal to 0. And if I want to correct for variation among people, so the inter-individual variation, for example, I go from 0.6 to 0.75. And that is then the value, grams per kilogram body weight per day, that a normal young adult needs to compensate for the nitrogen losses. And all this is expressed for animal-based protein. If you would go for vegetable-based protein, then I have an extra correction factor for the differences between plant-based and animal-based protein. This is the technique. And of course, there are limitations. So for example, we don't know the miscellaneous nitrogen losses. So these losses of hair and skin and etc., we don't know exactly how much it is. We also feel that the differences between intake and losses are quite small, certainly taking into account that the values for nitrogen intake and losses are quite big. So I can make quite strong mistakes during the measurements. Also, some nitrogen is not well measured. And we also see that some nitrogen in food or in urine cannot be measured by the techniques that we have. Yeah, so there's a problem in terms of analytics. There's a problem in terms of distinguishing the intake from the losses, and some losses can actually not well be measured. So quite some limitations in this approach. So there is a problem-based learning question, but we are not going to solve it in class, but you can think about it yourself. Just think that a person who is adult would like to stimulate muscle growth. So he would like to eat a lot of protein to get positive nitrogen balance in order to stimulate synthesis of muscles in the body. And so you eat a lot of protein. The question is, can I get more muscles by this? So think a little bit about the idea that a person is consuming a lot of nitrogen, that the nitrogen balance will become positive after a while, which is true. So positive nitrogen balance means more nitrogen is retained in humans. It means that more protein can be deposited. The question is, do you think that this process is very efficient, or is it not efficient? So why yes or why no? And explain a little bit your answer. So giving people an overload of protein, will it contribute to protein synthesis? And is that an efficient process for humans, or is it not? And explain it. Today we can actually measure all the different nitrogen streams in the human body. So we can measure oxidation of amino acids, we can measure the synthesis of body protein, we can measure the degradation of body protein from the muscles. We can do that in fasting state, so when people are not fat. We can do that in the fat state after people have taken in a protein-rich meal. We can do that at low dose of protein and at high dose of protein. And we can measure all these different pathways by use of stable isotopes. And you can see that when people are fasted, degradation pathways are significant. So it means that a lot of nitrogen amino acids are coming from the muscles, are released in the body tissue, and probably are being used to generate energy. In the fat state, the degradation is much smaller, and there is more synthesis occurring. So it means more body deposit is deposited. But at the same time, you can also see that the oxidation is significantly stimulated, much more than what you get in the fasted state. And this brings us to a little bit the requirements for total protein for the different age categories. For children up to 6 months who are in, let's say, taking up breast milk, you just measure the amount of breast milk that the child takes in. You measure the composition of the breast milk, and this will give you the recommendation for total protein. So that's quite easy, provided that the child is growing in a normal way. And so if you give enough breast milk so that the child can grow spontaneously, that amount of nitrogen you need is the recommendation. And it's set to 1.47 grams per kilogram body weight per day. If we start from 6 months up to 18 years old, so these children are growing, are increasing in body weight until they are adult, in that case we use the factorial method that I just explained to you. So we look at the nitrogen balance, all the losses that are occurring at maintenance, adding them all together, and then you get a value of 100 to 120 milligrams of nitrogen per kilogram body weight per day. You add a coefficient for growth, including an intra-individual variation, so the variation in growth speed within the child as a function of age. This is called intra-individual variation. You assume that the protein is consumed for about 70%. You know now why, I explained it before with this efficiency of utilization. And you also correct for the variation. In this case, the inter-individual variation between people. And then you get 0.9 to 1.2 grams per kilogram body weight per day for that age category. So you see that you are reducing. The recommendations increase for very small ages, for very, let's say, young people. When you're growing, then the recommendation goes down a bit. For adults, you also take the factorial method, so maintenance balance. You have an efficiency of utilization, correction for inter-individual variation. The value now becomes 0.75. You don't have to correct for a growth, which we had to do here. So that's why it is a little bit higher here. But if you are adult, then you don't need this growth. So you have 0.75 grams per kilogram per day. Males and females are the same. We don't know anything about elderly. So we assume for the moment that it's the same for young adults, but probably we need new studies to also evaluate protein requirements in elderly. You have to add extra nitrogen for pregnancy as well as for lactation, which you get from protein deposit, from protein in the milk, and from variation in birth weight, depending on the case. Okay, so this determines a little bit total protein. And then we come to individual amino acids. I think that is a little bit a more complicated one. Individual amino acids, there are several of them. Some of them are essential, some other ones are not. So we're mainly talking here about requirements for essential amino acids. And today for infants, this is still determined by looking at breast milk intake, measuring the amount of the amino acids you have to take in for a normal growth pattern, just the same as with total nitrogen and total protein. For children, the factorial method has been used in the past, the same as with total nitrogen. But today, the factorial method for children, especially for amino acids, is not used anymore because it has ethical restrictions. And you cannot, for example, deny a child to take in an essential amino acid because it could directly affect growth speed. So this is ethically not allowed anymore. So today, also for children, just the same as with the adults, the requirements are actually determined by the use of stable isotopes, which is much more sensitive and which will directly give us an idea about the requirements for essential amino acids. The article that explains more in detail how it works with the methodology is the article from Elango et al. You can find it online on the Euphora website, and I explain to you the most important principle. So listen carefully. It's a little bit difficult, but if you listen carefully, I'm sure you will understand. There are two ways of measuring it. The first one is called the direct amino acid oxidation method, which is this curvature. First it is flat, and after the recommendation, the requirement, which is this vertical line, it's going straight up. Yeah, so the knick that you see here in the line is the point where you can find the requirement for the amino acids. So this point is used in the direct amino acid oxidation methods. The second method is the indirect amino acid oxidation method. And there you see that the value goes down up until you reach the requirement. And after the requirement, it is horizontal. The two techniques are not the same, but they're very close. So I will start with the first one, the direct amino acid oxidation method. In this case, you will label the amino acids that you are following up. So it means that when we take up more of the amino acids, for example, leucine, then you will see that the output, which is actually the appearance of label at the level of the breadth, so you actually expire, in this case, labeled amino acids, will continue to be constant. So you will not see any change in what is excreted as long as you do not meet the recommended amount. So when we take up less than what we need, you can already imagine that all the amino acids will not be oxidized, will not be converted into CO2, but will actually be used to build up body protein. Everything will be incorporated in the muscles, so you will not find it in the breath and in the air, so you cannot measure it. That's why it stays constant. Okay? So the response is actually what you measure in the breath, in the output. So you will not measure anything in the beginning. As soon as you reach the recommendation and you go beyond that, so it means that persons will eat more amino acid than what is actually required, then the excess of amino acids, so the one that you don't need, is going to be oxidized. And this oxidation leads to CO2. The CO2 will go to the bread and we measure it. So that's why you can see that after the recommendation, there's a steady increase in the output, what you can measure in the CO2 in the bread. And the knick point between the two is equal to requirement. That's the first option of measuring recommendations. The second option is a little bit more difficult. We're talking about the same amino acids. So for example, we're talking about leucine. But now we're not going to label leucine, but we are going to label a second amino acid, for example, tryptophan. And this is called the indicator amino acid. And so that's why they also call it indicator amino acid oxidation methods. So we're going to follow up the behavior of the indicator amino acids as a function of the presence of the target amino acids, leucine. So as long as the target amino acid is lower than the recommended amount, then we see that also the tryptophan, indicator amino acid, will be built into body protein, into muscle protein. That's why the value goes down. As soon as you have this amount circulating in the blood, it can just go to the muscle and it can be used to produce body protein. The more of the target amino acid you give, the less we actually need, so the more is going to be expired, and so it's going to be burned down. So as soon as we get to the recommendation and we go beyond the recommendation, it seems that we cannot further use indicator amino acids to produce body protein. It's not possible because in that case, you will see that there is no further reduction, losses in this case of indicator amino acids. It's not lost anymore because you cannot absorb it anymore in body protein. You can only absorb it if you have here a certain amount of amino acid. If you go beyond the amino acid requirement, at that moment, the excess is just oxidized. And this also means that the indicator amino acid will not be used any further. And that's why the value stays stable. I hope it's a little bit clear. If it's not, just please read a little bit the article and ask me some questions afterwards in case you have a problem with the technique. So, but the two techniques, try to distinguish them from each other. They measure the same, so they measure the same requirements, but the approach is different. In the first technique, you label your target amino acid. In the second technique, you don't label the target amino acid, but you label an indicator amino acid, which is there in excess. And you just follow up the curvatures in both cases. If you find a knick, this is the place where you have the requirements. There's a third curvature here, but this corresponds more or less to what we said before. So you can look at growth speeds, you can look at nitrogen retention. So it's a more or less the nitrogen balance technique that I explained already in the previous slides. If you can understand this slide, you understand everything in the course, because this is probably the most difficult part that is there. So if you start measuring that, then you could look at adults. So you could look at the values outside the brackets. This is the value for the nitrogen balance, so the classical traditional technique, and the values between brackets for the different amino acids is done with the stable isotope measurements. And you can see very clearly, not in all cases, but in some cases, you can see that the values are much higher than what you get when you're measuring the nitrogen balance technique. So it means that with the new technology, you're actually measuring in a much more sensitive way. And so probably with the balance technique, we have an underestimation of the requirements. For infants, there's no discussion. You just measure the concentration and the amounts in breast milk. Right. So in this case, you know more or less how we can determine requirements for essential amino acids in living humans, infants, adolescents, children, adults, and elderly. So the last part is now going to talk about protein quality. So protein quality means what is the digestibility of the protein, what is the amino acid concentration of the protein, and this is necessary to know in order to understand to which extent it can compensate for the requirements. It's the same as what we did with energy, where we talk about energy value versus energy needs. Here we talk about protein value versus protein needs. The first parameter that can determine the protein value is the digestibility. So the way by which amino acids are released from the GI tract, are absorbed in the human body, and can be used for body metabolism. You can measure that by looking at the feces, then we call that a fecal digestibility, or you can look at the ileum, which is actually at the last part of the small intestine, just before you go into the colon. And you can just take a sample there from the GI tract. You can look at the composition, and this can be used to determine the digestibility of the protein. Fecal digestibility, as you already know, has the problem that there is nitrogen there that is not linked to the product itself, but which is coming from the body. Ileal digestibility can also contain partly protein that is coming from the body. So in order to correct for that, we determine the so-called endogenous amino acid losses. So these are the losses that are coming from the cells and from the mucus, from what is excreted in the GI tract, for example, from enzymes or from bile acids. And these losses are actually determined by the type of dietary protein, by the presence of fiber, and by the presence of so-called anti-nutritional factors. That could also influence the digestion process, and that could increase the number of losses in the GI tract. So if we can correct for endogenous amino acid losses, then you come out with a true value. We call that the true nitrogen digestibility coefficient, which is a digestibility which is corrected for the endogenous losses. It's the most correct thing that you can do. And you can measure that either at the level of the feces or either at the level of the ileum. If it's at the ileum, then we call it the true ileal nitrogen digestibility. If it's at the level of the feces, then we call it the true fecal nitrogen digestibility. Yeah, I hope it is a little bit clear. So you measure nitrogen in the food, you measure the nitrogen in the fecal material, you subtract the two and you divide by the nitrogen in the food. This is called the apparent fecal digestibility, so no correction. However, if you correct, then we call it the true nitrogen digestibility, and it could be an ileal one or a fecal one, depending on where you take the sample. The same with apparent, it could be a fecal or an ileal, whether you take the samples in the fecal material or whether you take it at the end of the small intestine. And the coefficient for digestibility is just taking the amount in the food minus what you get in the fecal material, divided by what you get in the food. And this is then an apparent fecal nitrogen digestibility coefficient. You can go to the course notes, and there you will find the exact formulas. And if you measure in the ileum, then you can have an apparent ileal nitrogen digestibility coefficient by taking a sample from the food, taking a sample at the end of the small intestine, and then dividing the two, and so subtracting the two and then dividing it by nitrogen in the food. So they measured all these coefficients. They do that in milk, they do that in soy, and then you can measure all these parameters, and then you can measure a coefficient. Yeah, so in this way, you could actually compare proteins just on the basis of their digestibility. In principle, if you correct all these endogenous losses, then the coefficients will come closer to each other. So if you want to have, let's say, sufficient difference, then it might be interesting to go for either an apparent or a true ileal digestibility coefficient. And you can see here the values. So clearly indicate which parameter you use in order to compare different types of proteins. Okay, I think it is now 3:15. I think the most important things are said. So the next time I will continue with explaining a little bit further the different scoring patterns, and we will also make the transition towards minerals. So good afternoon, everyone. This is the lecture number 7 from the course of Human Nutrition, where we will mainly deal with water balance, some remaining elements regarding nitrogen and protein balance, and we will also discuss the minerals, mainly sodium in relation to blood pressure and calcium in relation to osteoporosis. I think last time we finalized with a discussion on protein digestibility. And I think it was a little bit a difficult discussion because there are quite some formulas that you have to use for that. And I didn't show the formulas last time on slides, so it may have been a little bit difficult. So I will repeat this part again, and I added one slide that shows you the actual formulas so that it is more easier for me to explain it to you. So we are talking now about protein value. And protein value is actually a measure for the quality of the protein. So if you want to rank proteins according to their quality, you have to work according to the protein value. And in that value, you have two different parameters. The first one is related to digestibility. The second one is related to the amino acid composition. So we start with the digestion, the digestibility. There are different types of digestibility coefficients. We call them the apparent digestibility coefficient if you do not correct for endogenous amino acid losses. So all the nitrogen that is coming from the host, from the body itself, but not from the dietary foods, is called endogenous amino acid losses. If you don't correct for that, you call it an apparent digestibility. And you can measure it in the fecal material, or you can measure it in the ileum. In this way, we call it apparent fecal nitrogen digestibility or apparent ileal nitrogen digestibility. If you measure the endogenous amino acid losses, and in the course notes you can check it, there are a couple of examples on how to measure this. This fraction is mainly related to what is removed from the intestinal wall, so desquamation, like mucus and cells which contain nitrogen. Also the enzymes that are released into the GI tract for normal digestion, and the bile acids, which also contain nitrogen. So this is released during digestion. And of course, it is dependent on the type of protein you take, whether or not fiber is present, and whether or not anti-nutritional factors are present. An anti-nutritional factor will inactivate enzymes. So it means that the digestion of the proteins will be limited. And in this way, you get more nitrogen losses. The same for fiber, which can have more desquamation from the wall. And the dietary protein, whether it is a plant-based protein or an animal-based protein, will determine also the amount of losses that you get in the GI tract. The measurements can be done, for example, with protein hydrolysates, which means that you give a fully hydrolyzed protein, so almost 3 amino acids in the diet. And then at the end of the ileum, you just measure the amount of protein that is physically in the GI tract. The protein which is there is not coming from the diet, since everything in the diet has been hydrolyzed. So that intact protein must be coming from the host, so it is related to the endogenous amino acid losses. So this is one of the options. There are more techniques, but that's one of the popular techniques which is used to measure endogenous amino acid losses. If you correct for the losses, then you have a true digestibility. So you get an apparent if you don't correct. You have a true digestibility if you correct for the losses. And then you have a true ileal nitrogen digestibility or a true fecal nitrogen digestibility, depending on whether you measure in the ileum or whether you measure in the fecal material. To show that in the form of formulas, and it's more easier to understand, digestibility coefficient at fecal level, who is apparent, means that you will measure the nitrogen in the ingesta, so the nitrogen in the food, minus the nitrogen in the fecal material, divided by the nitrogen in the food. And you might multiply with 100 if you want it as percent, and this gives you the digestibility coefficient measured in the feces, while it is an apparent coefficient with no correction for endogenous losses. The same for the ileal digestibility coefficient, but now you replace the fecal sample by a sample in the ileum, so at the end of the small intestine. And it is also apparent since there's no correction for the endogenous amino acid losses. And if we do correct for it, then you just add here endogenous amino acid losses just behind the nitrogen ileum. And then you get a true digestibility. And so a true ileal nitrogen digestibility, or a true fecal nitrogen digestibility coefficient. So I hope it is sufficiently clear. It's not too difficult, but there are several definitions here coming together.